Good. I guess that's the sign, right? So, hello everybody, welcome. Is this mic working okay? Okay, excellent. My name is Tijs van der Storm. I'm a researcher at the Center for Mathematics and Computer Science in the Netherlands, CWI. I'm here today to talk about our programming language that we've developed over the last 7 years. It's called Rascal, and it's a programming language for metaprogramming. So, if you look at metaprogramming on Wikipedia, it actually has a quite nice definition, quite general. It's basically programs that consume, process, or analyze and maybe produce other programs. So it's really just programs where some kind of code goes in and something else comes out, and sometimes this is also code, right? And these things are quite well known within software development. You probably are all using meta programs. So we can think of code visualizers, refactoring tools, but also smell detectors or compilers, interpreters, tools that analyze metrics of other programs, and so on. So basically there's a large space of tools that just do something with source code, and most of that's also code, right? So, and these are meta programs. So if you look at the tools that are available to do some kind or some form of meta programming, there are various sort of independent tools that you could use for different kinds of things, right? So really simple lexical meta programming could be done, for instance, in awk. More complex stuff, you would use Antler or something. If you just want to search for some string, you would actually use grep. But if you need more complicated queries over sort of facts derived from your source code, you might want to use SQL. So all these tools and other tools, they are very good at one particular thing. And the problem is that most of the refactoring or metaprogramming applications I've shown on the previous slide often use a combinations of features. Some lexical processing, some analysis, some parse tree or structured rewriting. And so if you use different tools to do that, then you get an interoperability problem, right? So they don't integrate very well. So Rascal is our attempt at building a sort of unified language that addresses all these concerns in a single language, where these diverse concerns are all expressible and sort of easy to combine in a comprehensive tool. So yeah, so to make this a little bit clearer, let's have a hypothetical, maybe even pathological example where you do some grep on some some source code. You get some results of the matching regular expression. You want to import it into SQL to do some querying or joining or group by, whatever. And then you want to export that to some org script to actually generate something else from it, right? So, and here you can easily see that this is not a really nice way there is no nice way to sort of interconnect these independent tools. So in Rascal, we want really sort of address the whole scale of these things so that you're in one language using unified representations to do all that. Okay, so what is Rascal? It's basically a functional programming language, but with curly braces. So it looks like Java to some. It even looks imperative, but mind you, underlying all data is immutable, so there are no aliasing problems and so on. It runs on the JVM. So if you were at the keynote this morning, you know, David Nolan saying that Clojure tries to go where the mainstream goes. We have the same idea, so we want to sort of take benefit from the large Java ecosystem that is around that. So we run on the JVM and have also easy interaction with anything in Java. We have a command line REPL. We also have an IDE based on Eclipse. You can download it if you want. The source is on GitHub, and we have an update site for Eclipse. And downloading the command line version is just a single jar. So if you hate IDEs, you can still use Rascal. Okay, so how do we achieve this integration? Well, basically, you could say actually that Rascal is it's a general purpose programming language in power. It's Turing complete, and you could do technically everything in it, but it's really also a domain specific language. So we have a lot of stuff built in, particularly designed for this metaprogramming domain. So, for instance, we have a lot of built-in data types, like concrete syntax, data types for concrete syntax trees, which are sort of abstract syntax trees, but you don't throw anything away. We have abstract syntax trees, of course, but we also have a data type for defining source locations, because often you do something with some part of the source code in your processing. And then we have pattern matching, really powerful pattern matching constructs to do pattern matching against all the data types. So we can write patterns against all values that are present in Rascal. And I will show down the line using some live coding. I hope to sort of show some cool pattern matching features. And finally, to sort of address more the analysis kind of thing, like the queries or the aggregation kind of stuff that you might want to do, we have comprehensions over all collection types. And all collection types means sets, relations, n-ary relations, lists, and maps. So that's sort of one way, one aspect of how we try to integrate all these tools. More specifically, we have some, I think, unique language features. So one of them is integrated syntax definition and parsing. This means that you can write context-free grammars as part of a Rascal program and get your parser for free. We have built-in primitives for tree traversal. You can imagine that in many source or code transformations, you have to traverse syntax tree structures. So we have a built-in feature for that. We have sophisticated pattern matching operators. I already hinted at it. So this is not your grandfather's father's pattern matching, but it has concrete matching, deep matching, list matching, set matching. I will show some of these examples, but I'm afraid I can't go in too much detail there. And finally, we have sort of relational data types that allows you to do graph-based analyses. For instance, dependency graphs or control flow graphs, data flow graphs. We think that these are very nicely represented using relations. Okay, so enough talking. Let's write a meter program. So here's a really simple meter program. You could call it a smell detector. We want to find public fields in some Java code, right? So we could do grep, right, and write a regular expression that matches public, blah, 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 blah. And then you get a list of results. But there's a risk that this is very imprecise, right? Because grep will also match in comments or in string literals. And maybe there are different forms of declaring a public field, and you have to write horrible regular expressions. So this is very low tech, but no, we're not going to do that. So we could do Handler, download the Java grammar and sort of start parsing Java, and then write a visitor and have to write ugly if statements to sort of select, okay, this is a field and the modifier is public and blah, blah, blah. So I think that's too much work. You may differ there, but so let's see how we do this, how we can do this in Rascal. So I'm now going to demo mode. So I hope this is all readable. Yes. Okay, so I have a module here defined in Rascal in our IDE. It's called find fields. We import the grammar, the context-free grammar of Java 1.5 in this case. I import also the library to access the parse tree data types that are built into Rascal, and I need that because I want to get the source locations of certain substrings, subtrees in my parse trees. So now I'm going to sort of write this function, which now has an empty body. But before that, I just want to show you this. So this is the REPL. And I've also imported the grammar here. And now here you see a declaration or a variable declaration that assigns a source location to this variable source. And I told you source locations are built in, and also the IDE knows about it. So I can actually click on it, and then it will open the file that sort of corresponds to that source location, right? So this is a simple Java file with some public fields. So of course I can also use this source location to actually parse the structure, right? So I've imported the Java 1.5 grammar, and in that Java 1.5 grammar, there's a start non-terminal. It's called compilation unit. And I'm now going to parse this source location using that non-terminal. And that works with this notation, which is almost like a cast. But if you feel like this is casting, like in Java, casting in Rascal is parsing. So that basically says it all. And then I give it the source location, and then after some, this is only the first time, don't worry, it's generating the parser. So, and what you get is actually a typed parse tree, typed as the non-terminal of that grammar. In this case, it's the start non-terminal compilation unit. And then down there, you see the literal rendering of the source code itself. So you might think, okay, this is just the string, right? And that's because that's true, because it's a concrete syntax tree. So it has all the information that's there, all the white space, all the comments is there. And you can actually see that the REPL actually knows that this is a parse tree and not just a string, because you see the syntax highlighting, right? I hope this is visible. So the keywords are highlighted there. Okay, so this will be our example input to the find fields example. So let's write this code. So here's this function, public fields. In goes a compilation unit. Out comes a list of log, sort of corresponding to the locations of these public fields. So since we need a list, I'm going to define it using a list comparison. Let's assume I'm finding a field, and then I want the location of that. And now I have to find all the public fields within the parse tree of the compilation unit. I'm going to use a pattern match for that. It's a concrete syntax pattern match, and I'm writing it like this. I don't care about the type, but I do care about the field. Let's make this a little bigger. So this basically is a field declaration, and I'm going to find it in the compilation unit. Right, so what this states is using the slash, it basically means anywhere in the tree find instances, subtrees that match this pattern. This is the pattern that I'm looking for, which is a concrete pattern. So it's not like a prefix notation AST based pattern, but I'm using the language that I'm processing, right? So Java in this case. And you can again see this from the syntax highlighting. This pattern actually is a parsed representation of a pattern over some Java source code. So it's also, the matching that's happening here is also modulo layout. So basically the layout, the white space and the comments that are in the source file or in this pattern are basically ignored when matching, so that you can find you basically are matching against an abstract syntax tree but using concrete syntax notation. Okay, so this completes the program. Now let's run it. Import find, and let's save it. Find fields. Oh, it's called find fields. So now we run it on the source. On the source, and then something is wrong. Oh, wait. Okay. That was the location. So make a parse tree. And then, okay, there we have it. So we have this list of locations. I can click on it, and then you also see that it actually accurately captures the source location of this specific field declaration, right? So the source locations doesn't cover just resources on the file system or something, but it really captures areas in your source code. Okay. So this was basically a warm-up thing, right? It matches, it fits on one slide. It's almost a one-liner. So what have we seen? So we have a compilation unit, a typed compilation unit that goes in. I search for matching nodes within that compilation unit using this pattern and this / operator. And then I match against any kind of subnode in this tree to find the field that is actually public. And then I return a list of source locations in a list comprehension. Okay, so this was sort of easy, and you could say, well, you know, these false positives of grep, that's good enough for me. Let's make it a little harder. So let's say we're going to do high fidelity source to source transformation, and high fidelity means that we want to preserve as much of the source code layout and shape as possible. And the task now is not to just find the public fields, but actually to eliminate them. So, and there are two things that we need to be doing here. So we make the public fields private, and we add a getter method and a setter method, and then you know, we forget about the assignment sites. That's for another talk. Okay. So let's do this. So I have another module here. So now we're going to transform a compilation unit. So in goes a compilation unit, and also out comes a compilation unit. So let's start. I'm now going to use the traversal feature of Rascal. I'm going to visit the compilation unit. And since I'm actually I'm going to rewrite the class bodies themselves, because I need to insert additional methods next to the field declarations. I cannot sort of replace one field declaration with the new field declaration and the other method, so I need to insert it in its context. So I'm going to match on a class body, and then that starts with a curly, and then I also have to match the context of the class body, which is any number of class body declaration. And then when I find a public field there, now I am interested in the type IDF, semicolon, and then there may be body declarations after it, and I have to have the closing thing. And now I'm going to rewrite it. So let's just rewrite it to the same thing. So you see now I've written a pattern that matches any kind of class body using a concrete pattern, and the star things indicate that this is some kind of search, right? So this is called list matching, where I'm actually searching for a public field anywhere in the list of class body declarations of my class file, right? So now, since I do have the context, I can actually restore it. So in the other part of the rewrite, so I'm putting it here, but now of course I make the field private, and I'm going to add an edit methods, right? Void set, okay, the setter should be public, ID setter, type TX, and then I assign it to the field, and I add the getter where I need the T again, ID getter, which has no arguments, and then I return this dot IDF. Okay, so now the only thing is that I don't have identifiers for the getters and the setters yet, so I'm going to do that in a side condition. When ID setter is ID, I use this parse notation again, and then I'm skipping over capitalization now, but you get my meaning, right? And then ID get F. Right. Okay, so we've written a transformation that visits the whole program, and anywhere it finds a public field in some class body, it will replace it with a private field and the additional methods. So let's try to run it. So we have our input program, and now I'm going to transform the fields. It needs to import again. Okay, transform fields on PT. Okay, So it's almost correct, right? So it didn't do the last one. So, and that's actually because this visit statement, the way I invoked it here, it sort of visits every node once, right? So when it visits the class body, it finds the first thing and then it forgets about the other thing. So there's one feature of this visit statement is that you can annotate it with strategies, and there's a built-in strategy that sort of keeps on applying these rewrite rules until there are no more matches. And this is called the innermost strategy. So I write it like this, and now it rewrites them all, right? Okay. So brief recap. We match the source pattern using list matching, right? So it tries to find this public field inside this list of class body declarations. And then we actually construct a new body, which is of the same type, class body. And then we insert the new getters and the new getter and the setter and change the field declaration itself from public to private. And then we need these getter and setter identifiers. We use the parse cast operation to create them, and then we use the innermost strategy to keep reapplying these rewrite rules till the end. Okay, so what we've seen now is that there's basically a sort of perspective here of making tools to, you know, improve or better understand existing programs, right? So we've made a small smell detector, and we made a small refactoring, if you could call that. But it's all from the perspective of, okay, there's some existing source code that I want to improve or understand. However, there's also another use case for Rascal, which is actually more from the forward engineering perspective, where you actually want to build new languages to make software construction better. And these new languages are often domain-specific languages or little languages, if you like. And this is where Rascal as a language workbench comes in. So Rascal is a language workbench, and what is a language workbench? Well, it's basically a compiler on steroids, right? So yes, you can build your compiler, but you can also build IDE support for your language. So it basically allows you to create integrated development environment for your new language. So, and this is a good match, because if you look at language implementation, you see immediately, or maybe not immediately, but I think this is obvious, is that language implementation is a kind of metaprogramming, right? If you build a language or a compiler, you need some kinds of analyses, you need transformations to actually implement your compiler or the type checker or whatever you like. So we can actually use these metaprogramming features built into Rascal really well in this domain. So I'm not going to live code the whole DSL now. That would be great, but I do have a small example. So this is Martin Fowler trying to sell design patterns. He's also known for writing this massive book on domain-specific languages. And in this book, he uses this state machine example language where you can define sort of Gothic security protocols where you have to sort of switch a lever, open a drawer, and then some secret panel opens and whatever. And we've implemented this in Rascal, and I'm going to demo that now. So let's close this one. Don't need it anymore. Where are we? So here you can see a simple editor that, let me also show the outline. Yeah, so here's a simple editor of a textual representation of this state machine language, right? So you have some event declarations, you have some reset events, it doesn't matter right now. You have commands defining some special tokens that need to be sent over some wire. And then you have state definitions that say, okay, whenever I enter into a state, perform these actions, and there are these transitions if certain events happen, right? So this is a simple language, but it still already has some quite nice IDE features, right? So I have the syntax highlighting, I have an outline thing that sort of is linked to my source code. I have hover, jump to definition features. I think if I just hover over it, I get also documentation. Well, yeah, so you get hover documentation. If I make a mistake somewhere, then the type checker, the static checker of this state machine language will sort of uh, find errors and also mark them in the IDE, right? So it's not like the type checker says no or gives you some basic errors on the command line. No, you get them nicely in the IDE. Um, More advanced features include like a rename feature. I can rename an identifier here, and let's say I rename it to idle. And then, of course, this what enables this is that basically these transformations that I've shown earlier, they work on the concrete syntax trees, right? So if you want to build a refactoring, the first thing you need to be sure of is to not throw away layout and comments, or at least try to do it as much as possible, because as soon as you pretty print the source code, your developers won't be happy, right? We know this from experience. Okay, final thing of this language. Of course, we need the compiler itself too. So if I save it, then it basically is compiled to Java that can be executed. I mean, this is sort of mock-up Java, but I hope you get my meaning. Okay, so to conclude, so this DSL implementation, I've not shown all the features yet of it, but basically defining the concrete syntax, the abstract syntax, an unparsed function, desugaring, checking, outlining, hyperlinking, compilation, visual simulation, rename refactoring, also a parallel merge operation where you combine two state machines together. You can all write that down in around 532 lines of code. And I think that is, I mean, that's not an absolute yardstick, of course, lines of code, but it does show you that with minimum effort, you can get a long way, and this allows you to prototype your language much better, to iterate more quickly, and to be quicker in showing it to users in some sort of workable form instead of just on the command line. Okay, final words. So you might think, okay, Rascal, this is cool and fancy. I hope you think that, but this is an academic language. Yes, it's an academic language, but we're working on adoption in companies, and we're also using it in teaching courses on software analysis. I'm using it in courses on software construction based on DSLs. We have not many papers on Rascal itself, but most of the papers that our group produces are sort of possible because of Rascal. So Rascal is for us a really strong research tool that is behind many of the papers that we write. One particular area is that we do corpus analysis, where we analyze millions and millions of lines of Java code and C code. But we also use it to build DSLs. So we have students working on Rebel, which is basically an attempt to redo the ING bank. And that's getting traction there. We have a project starting with Philips. Micro Machinations is a graphical DSL for doing game economies. A little more long ago, we had Derek, which was a DSL for digital forensics, which is actually in use at the Dutch CSI. So we're getting there, and we're very open to any user that I mean, we invite everybody to try it out. We have a Stack Overflow channel, etc. So if you want to know anything, please contact me. Okay. So metaprogramming, we have a couple of tools, lots of tools to do these things, but they don't integrate very well. We think that in Rascal we have sort of bound together numerous existing language features in a unified whole. You can use it to do sort of reverse engineering tasks or metaprogramming, and the basic components that sort of enable this are really powerful pattern matching, built-in primitives for traversal, and of course built-in syntax definition and parsing. And finally, it can also be used because of that as a very nice language workbench where you can try and prototype and iterate your language designs very quickly, including IDE support and so on. Thank you very much. Questions? Yes, Patrick.
So I wanted to ask about the concrete patterns. A couple questions.
Mm-hmm.
First, first about the space skipping you
Mm-hmm.
talked about. Does this only work for context-free languages?
Yes.
Does the grammar have to say, here's what a space is in this language?
So basically the grammar has a special sort of language construct for saying this is layout, right? And then it skips it, so you don't have to specify it everywhere in your grammar rules. So it's like an aspect.
So you couldn't do it for Python or something, or Haskell?
Not yet. So last onward we had a paper on data dependent parsing, and that then you can. Oh, sorry. Yeah. So it's about layout skipping. Does it work for indentation sensitive languages? Currently, no, but we have a paper on how to do indentation sensitive parsers, and we just need to integrate it in our main parsing framework. Yes.
When you were making program transformations in contexts that allowed many things, a list of things, I saw that you required the user to instead match on the parent and then make a replacement there, and that's the upside is that they can actually make that program transformation, but the downside is then it's inconvenient for the user, and it also allows invalid transformations like non-empty contexts, right? Could be replaced with like 0 items. My question is, did you look into performing transformations based on like a named context that says this context only allows one item, or this context allows one or more items?
I'm not sure I completely understand. I think the question is whether you could write transformations like this, where you go from one to many without having specifying the context. Yes, so yes and no. So currently, this is what you have to do, because otherwise your transformations become syntax unsafe, right? Basically, the idea of this arrow, the arrow to the right, is that thing of type T goes to thing of type T, right? And if you go from field deck to field deck star, or class body deck star, that's not type preserving. So we are constantly thinking about how we could address such use cases in a more less boilerplatey way. But for now, actually, we just you have to do this.
But how do you deal then, for example, with JavaScript with semicolon insertion or like with go boolean?
Okay, so how do you deal with semicolon insertion in Java, JavaScript? Yeah, so JavaScript has such a terrible grammar, right? I mean, the language is, well, it's defined in terms of parse errors, which is really annoyed, right? So uh, one thing you could, if you get a grammar, so we have a grammar of JavaScript, but it requires semicolons. But if you make the semicolon sort of part of the layout, right, you sort of say that it's like white space or it's like a comment, then basically it doesn't matter whether you write the semicolon here or not, because it will be ignored anyway, right? So ignored, but possibly transferred, so you don't remove them all the time. Yeah, I don't know where to start. Oh, okay.
Does the transformation understand that scoping? So you have a public field called if x, an argument or method called x, and then only want to transform the public field in some case. Does it understand that?
So the question is, does the transformation understand lexical scoping? The answer is no. We did do some experiments where we fixed the sort of name capture that you could create in the syntax-based transformation after the fact. So there is an eCoop 2014 paper by Sebastian about this. Yes?
Yeah, you mentioned something very briefly about comments.
Yes.
Can you say something more about what you do and how successful you are at it?
You mean about about preserving comments? So yeah, so good question. So if you don't touch anything, then comments are just preserved, right? So if for instance comments outside this class body, they will be just be preserved. I mean, in outside of this pattern, so to speak, right? Currently, the comments are always in between things. So in this rewrite, the comments that are in between the class body declarations would have to be manually reinserted, because basically the term construction here sort of creates new layout, right? It uses the layout of this pattern, because otherwise you cannot know what kind of layout to choose. For all the other locations, it will just be there because it's part of the parse tree that is not touched. So I hope that answers the question. Okay. Yes, Jeremy?
You mentioned thing about visual simulation and having to support that. Does that go as far as like having a debugger for your DSL or not quite?
Not yet. So this Miss Grant language has a sort of, yeah, you could say custom debugger. So we try to also take visualization as part of meta programming, and so this uses our sort of old, not so pretty generating pictures visualization library, but it allows you to do things like this, and then sort of you visualize the state machine, and then you can click on these events, and then stuff happens. So this is part of the 532 lines of code. So there's a lot of stuff possible, and basically I mentioned at the final slide this micro machinations language, which is a graphical language for game economies. That's all built on top of this framework. So I think if you Google for micro machinations, you can find stuff about it. Yes?
If I were to use Rascal for big corpus of software projects from third parties, I mean different languages, computer compiling probably,
Mm-hmm.
what kind of
So the question is, if I use Rascal on some source code from the wild that might not even compile, what kind of trouble would I get? So yes. So our standard library has a number of grammars for some languages like Java, and we have also an Eclipse interface for Java. We have a JavaScript grammar with semicolons. And there are, so the idea is that the grammar formalism is modular. So there's also work being done right now on creating a COBOL grammar, which exists in gazillion dialects. So basically, the idea is that you start with some core COBOL, and then you sort of modularly add stuff for your specific IBM something something version. And so the idea is we're definitely targeting this use case, but the sort of the joke is that the grammar or the parsing is always the problem, because you don't know what the compilers do. So all grammars you find out there are wrong. All documentation is wrong. All specifications are wrong. So a lot of engineering goes into getting the grammar right. But I also must add that it really depends on your application, right? Sometimes you only want to find the if statements in some COBOL code, and then you can actually cheat and make a simpler grammar, a sort of island grammar that only matches parts of the source code. Yeah. Yes?
Can you cross language barriers? Can you, for example, take Java code and make Rascal rewrite it in JavaScript?
Yeah, so that would just be a different compiler for Java that's implemented in Rascal. Sorry, the question was, can you compile JavaScript to Java or the other way around, right?
Yeah, basically rewrite it.
Yeah.
Syntax in one language and
Yes.
the other.
Yeah, so basically this one was source type preserving, right? From compilation unit to compilation unit, but you can easily write a function that takes a compilation unit and produces the JavaScript compilation unit, right? I mean, it's not easy. I mean, it's a lot of work, but yeah. So there was a question, Alex?
Is Rascal bootstrapped?
The parser is bootstrapped. So Rascal itself, the parser of Rascal is bootstrapped in itself, and we're currently. So what I've shown is, sorry, the question is Rascal bootstrapped? Our current what I've shown you is based on the Rascal interpreter, which is sort of our way of getting off the ground. We're currently working on a compiler, and actually this is almost finished, and there it's really bootstrapped, because actually the interpreter does static type checking at runtime, but the compiler does static type checking, and we wanted to write the static type checker in Rascal itself, because, well, that's what we built Rascal for, so we need to do that. So it's almost there. Yes?
Can you customize like error output? For example, if your program is not valid, for example, right, for given syntax, so could you just customize, give nice error response?
Okay, the question is whether we can have good error messages for parse errors. Currently, no. So you get parse error at some location. And that is a consequence of a general parsing algorithm behind it, which is sort of messes up sort of any kind of locality where you are in your parser state. So it's ongoing work to make this better. Any more questions? Okay. Thank you again. We have abstract syntax trees, of course, but we also have a data type for defining source locations, because often you do something with some part of the source code in your processing. And then we have pattern matching, really powerful pattern matching constructs to do pattern matching against all the data types. So we can write patterns against all values that are present in Rascal. And I will show down the line using some live coding. I hope to sort of show some cool pattern matching features. And finally, to sort of address more the analysis kind of thing, like the queries or the aggregation kind of stuff that you might want to do, we have comprehensions over all collection types. And all collection types means sets, relations, n-ary relations, lists, and maps. So that's sort of one way, one aspect of how we try to integrate all these tools. More specifically, we have some, I think, unique language features. So one of them is integrated syntax definition and parsing. This means that you can write context-free grammars as part of a Rascal program and get your parser for free. We have built-in primitives for tree traversal. You can imagine that do something with source code, and most of that's also code, right? So, and these are meta programs. So if you look at the tools that are available to do some kind or some form of meta programming, there are various sort of independent tools that you could use for different kinds of things, right? So really simple lexical meta programming could be done, for instance, in awk. More complex stuff, you would use Antler or something. If you just want to search for some string, you would actually use grep. But if you need more complicated queries over sort of facts derived from your source code, you might want to use SQL. So all these tools and other tools, they are very good at one particular thing. And the problem is that most of the refactoring or meta programming applications I've shown on the previous slide often use a combinations of features. Some lexical processing, some analysis, some parse tree or structured rewriting. And so if you use different tools to do that, then you get an interoperability problem, right? So they don't integrate very well. So Rascal is our attempt at building a sort of unified language that's mutable, so there are no aliasing problems and so on. It runs on the JVM. So if you were at the keynote this morning, you know, David Nolan saying that Clojure tries to go where the mainstream goes. We have the same idea, so we want to sort of take benefit from the large Java ecosystem that is around that. So we run on the JVM and have also easy interaction with anything in Java. We have a command line REPL. We also have an IDE based on Eclipse. You can download it if you want. The source is on GitHub, and we have an update site for Eclipse. And downloading the command line version is just a single jar. So if you hate IDEs, you can still use Rascal. Okay, so how do we achieve this integration? Well, basically, you could say actually that Rascal is it's a general purpose programming language in power. It's Turing complete, and you could do technically everything in it, but it's really also a domain specific language. So we have a lot of stuff built in, particularly designed for this metaprogramming domain. So for instance, we have a lot of built-in data types, like concrete syntax, data types for concrete syntax trees, which are sort of abstract syntax trees, but you don't throw anything away. I guess that's the sign, right? So, hello everybody, welcome. Is this mic working okay? Okay, excellent. My name is Tijs van der Storm. I'm a researcher at the Center for Mathematics and Computer Science in the Netherlands, CWI. I'm here today to talk about our programming language that we've developed over the last 7 years. It's called Rascal, and it's a programming language for metaprogramming. So, if you look at metaprogramming on Wikipedia, it actually has a quite nice definition, quite general. It's basically programs that consume, process, or analyze and maybe produce other programs. So it's really just programs where some kind of code goes in and something else comes out, and sometimes this is also code, right? And these things are quite well known within software development. You probably are all using metaprograms. So we can think of code visualizers, refactoring tools, but also smell detectors or compilers, interpreters, tools that analyze metrics of other programs, and so on. So basically there's a large space of tools that just addresses all these concerns in a single language, where these diverse concerns are all expressible and sort of easy to combine in a comprehensive tool. So yeah, so to make this a little bit clearer, let's have a hypothetical, maybe even pathological example where you do some grep on some some source code. You get some results of the matching regular expression. You want to import it into SQL to do some querying or joining or group by, whatever. And then you want to export that to some org script to actually generate something else from it, right? So, and here you can easily see that this is not a really nice way there is no nice way to sort of interconnect these independent tools. So in Rascal, we want really sort of address the whole scale of these things so that you're in one language using unified representations to do all that. Okay, so what is Rascal? It's basically a functional programming language, but with curly braces. So it looks like Java to some. It even looks imperative, but mind you, underlying all data is